Welcome to the Explainer. Today, we're diving into something that, honestly, it sounds pretty simple at first, right? Counting. But we're actually looking at the structural logic of the universe here, the mathematics of counting. We're going to use our source materials to totally demystify some of these complex counting principles and really unlock exactly how probability works behind the scenes.
To get us started, I want you to just picture a standard shuffled deck of playing cards, just your average 52 cards. Now, ask yourself this. How many different ways can you arrange that simple deck? It seems like a very straightforward question, doesn't it? But let your brain chew on that scale for just a second. If you started writing down every possible unique sequence of those 52 cards, how long do you think it would take? Well, the answer is so unfathomably vast that it literally defies human intuition. By the end of this explainer, not only will you understand exactly how to calculate massive numbers like that, but you'll understand the pure logic dictating them.
So here's our roadmap for today. First up, we've got the basics of counting. Next, permutations. Third, combinations. And finally, something called the pigeonhole principle. Let's build up your counting superpower step by step.
All right, Section 1, the basics of counting and the multiplication principle.
Okay, to really master counting, we have to start with sequential tasks. If you can perform one action and then immediately perform a second action, how do you mathematically combine them? Well, this classic tree diagram demonstrates the multiplication principle perfectly. Notice how we start with just a single point right at the top. Now, when performing task 1, we branch out into a few distinct possibilities. But here is the real magic. For every single choice we make in task 1, an entirely new set of branches opens up for task 2. You don't add the possibilities, you multiply them. If task 1 can be done in, say, n1 ways, and task 2 in n2 ways, the combined sequence is simply n1 times n2. It's all about compounding choices.
And this brilliantly illustrates just how incredibly fast those numbers grow in real life. Take a look at this number right here, 26,000. Our source text provides this perfect everyday example of the multiplication principle in action. Imagine a computer system password, but it consists of just one single letter followed by 3 digits, and it allows repetitions. Using our principle, we know we have 26 choices for the letter, right? And 10 choices for each of the 3 digits. So that's 26 times 10 times 10 times 10. Boom, 26,000 unique password labels from just a tiny 4-character sequence. Crazy, right?
Moving on to Section 2, permutations. This is for when order matters.
So, in a permutation, the exact sequence of your items is absolutely crucial. If you change the order, you completely change the result. To navigate this, we need to decode a special mathematical key, the factorial. Denoted by an exclamation point, n factorial basically just means taking an integer and multiplying it by every whole number below it, all the way down to 1. So, for example, 4 factorial is 4 times 3 times 2 times 1, which equals 24. This simple little function is the engine that powers our permutation formulas whenever we draw items from a set without putting them back.
The crucial point here is seeing this engine actually in action. Remember our deck of cards from earlier? Suppose a dealer hands you 5 cards from a shuffled 52-card deck, and we actually care about the exact order each individual card was dealt to you. This is a permutation of 52 objects taken 5 at a time. Using our factorial logic, the math is 52 times 51 times 50 times 49 times 48. That leaves us with over 311 million specific ordered hands. Just by tracking the exact sequence of 5 cards, the possibilities just absolutely explode.
But wait, what happens when some of the items in our group are literally identical? Our source text uses a really fantastic example to explain this constraint using anagrams of the words banana and Mississippi. Think about it. If you just swap 2 of the A's in banana, the word still looks exactly the same to us, right? They are totally indistinguishable. So to find the true number of unique arrangements, you calculate the factorial for the total number of letters, sure, but then you must mathematically divide out the duplicates. You divide by the factorial of each repeating letter's count to sort of strip away those identical hidden permutations.
Which brings us to this highly surprising number. How many unique, distinguishable ways can you rearrange the 11 letters in Mississippi? Well, there are 11 letters total, which gives us an enormous 11 factorial. But we have 4 I's, 4 S's, and 2 P's. By dividing the total by 4 factorial times 4 factorial times 2 factorial, we effectively strip out all those meaningless swaps. The result shrinks way down to exactly 34,650 unique words. It's just a really beautiful way that mathematics forces order onto chaos.
All right, section 3, combinations. This is where order doesn't matter.
So what happens if we remove the strict constraint of sequence completely? Let's explicitly compare the two so it really locks into your brain. Think of the letters A, B, and C. In a permutation, ABC is fundamentally different from CBA. They are two distinct sequences, kind of like two different passwords. But in a combination, ABC and CBA are the exact same subset. It's like a group of friends going to the movies. It really doesn't matter who got in the car first, right? It's the exact same group of people. That distinction is the absolute crux of counting logic.
The text we're drawing from explains this relationship brilliantly by breaking it down into two logical tasks. To generate a permutation, you can actually just think of it as a combination in disguise. Step 1, you choose a completely unordered subset of elements. That's your combination. Step 2, you arrange those chosen elements into a specific order. And that's a permutation of the subset. Because we already know how to calculate the total permutations, we can actually just work backwards to isolate the combinations.
And that logic leads us directly to the combination formula. Now, don't let the mathematical notation intimidate you here. Let me act as your translator for a second. NCR stands for the number of combinations from n total items, choosing R of them. To calculate it, you take the total items you have to choose from factorial, that's the n fact on top, and you divide it by two things, the factorial of what you did choose, which is r fact, and the factorial of what you left behind, which is n minus r. That denominator acts like a filter, mathematically erasing all the different orderings that we frankly no longer care about.
Let's go back to our 5-card poker hand for a second. When we cared about the exact dealing order, we had over 311 million permutations, remember? But in real life, when you're actually holding a hand of cards, you do not care about the order you receive them. You just care about the final hand. By applying our combination formula, 52 total cards, choosing 5, we filter out all those identical hands that have just been rearranged. That massive 311 million drops dramatically to just 2,598,960 distinct 5-card hands. That is the true power of ignoring order.
Finally, Section 4, the pigeonhole principle, pure logical guarantees.
Okay, let's transition away from counting formulas and move into a completely different framework. We are stepping into pure logical guarantees with something delightfully named the pigeonhole principle. Now, I know it sounds trivial at first, maybe even a little silly, but it packs an unexpected, massive analytical punch. The principle states exactly this. If you have n pigeons and you assign them to m pigeonholes and there are strictly more pigeons than pigeonholes, then it is mathematically guaranteed that at least one pigeonhole must contain 2 or more pigeons. It's an existence proof. Our textbook gives a totally relatable example. If you gather any 8 people in a room, you are guaranteed that at least 2 of them were born on the exact same day of the week. Why? Because there are 8 pigeon people but only 7 pigeonhole days of the week. Somebody has to double up.
Let's see how this builds into some really beautiful visual geometry. Notice this hexagon with sides of length 1 divided into 6 equilateral triangles. Those 6 triangles are going to be our pigeonholes. Now, imagine randomly dropping 7 distinct points, our pigeons, anywhere inside this hexagon. Because 7 points are going into 6 triangles, the pigeonhole principle guarantees that at least one triangle simply must contain at least 2 points. And because the sides of these triangles are exactly 1 unit long, those 2 points can absolutely never be farther apart than 1 unit. Boom! We just proved a complex geometric boundary using literally nothing but the logic of counting pigeons.
And that brings us to the end of our journey today. We've gone from simply multiplying tree branches to manipulating millions of card hands, all the way to proving geographic inevitabilities using pigeons. The mathematics of counting isn't just about large numbers, you know? It's the invisible framework that dictates the rules of our reality. So I want to leave you with this question. Look around the room right now. What hidden mathematical guarantees, combinations, and pigeonholes are hiding in plain sight in your daily life? Take these building blocks, look really closely at the world around you, and I guarantee you'll start seeing the math everywhere. Thanks for learning with me today.